Inside this treasure chest are some of the highest quality lithium iron phosphate cells on the market today. I would love to use them for my solar off-grid system to power my entire house when the sun doesn't shine. But first, we have to unbox them out of the crate, unbox them out of their original arrangement, and then rebox them up into something that's more useful. Here we go. Hi, I'm David and welcome to my channel where I'm on a mission to take my house and garage completely off-grid. Over the last several years, I've been building up the entire solar off-grid system. I've got a great solar array in the backyard, I've got an excellent high-quality Schneider inverter on the wall, and I've even got some Army generators to provide backup just in case we have long stretches without sun. But the part that is usually lacking is the energy storage, the battery. And that's because the battery can be the single most expensive component of the entire system. When looking at home energy storage, you typically have your choice between either buying the pre-built battery or DIYing and building your own. I've tried both and both have their pros and cons. When I've purchased some server rack style batteries, they're great because they're ready to go right out of the box, they're already tested, and they work well. But they cost about $300 per kilowatt hour. When you build a DIY style battery, you might be able to do it for about $150 per kilowatt hour when you're done, but you're typically buying used cells that have already spent a life, like on the road, in a car, and they might be degraded. They might not last as long. But inside this, this crate, which we're about to take out, there are some brand new cells, and not just any. These are the highest quality lithium iron phosphate cells on the market today. We will have to unbox them and then unbox them out of their arrangement that they're currently in order to reconfigure them to work for us. But if we can do that, we'll have something that will last a very long time. And in the end, I think I'm going to be able to do this for about half the cost of a pre-made server rack style battery, or roughly $150 per kilowatt hour. If we can pull this off, it will be safer than 18650s or used electric car batteries, and it's an excellent option to get a lot of kilowatt hours of storage for the least amount of money. Nice. It's not just cardboard. They got a plywood frame too. Backside. Looks like a pretty thick steel base that it's sitting on. Fairly thin plastic cover. Yeah. All of these are for air to vent through. Over here's the front. I bet this fan is blowing in, and then it pushes the air out past each cell. These are each individual cell. So these are 280 amp hour cells, lithium iron phosphate, 3.2 volts each. This assembly could have been used in some kind of really high amp application. So the way this type of assembly works, it does not have a true BMS or battery management system. Instead, it has this, which is a BMU or battery management unit. It's collecting data and then sends that data up to some higher level computer, which would have been one central higher level computer for, I don't know, however many of these modules they'd have strung together. So what that means is that we'll have to add our own BMS. I don't know how these are attached yet, but it's probably just a push-in. This is the simple forked tool that I'm using. 3.292. 3.292. Oh my goodness. Wow. Oh, that is perfect. That doesn't get any better than that. Let's check our voltage for the whole pack. 65.88 volts. Now down here at the front, We probably don't have any voltage up here unless we were to attach the safety disconnect. So let's find out. Yeah, no voltage. And let's see what happens if we put the safety disconnect in. Looks like it's going to go this direction. Nice. And now let's check our voltage. And 65.9. Well, before I start messing around with this too much, I think I might take off this jumper on the rear. Let's see how it's attached. I'm curious how much torque it's going to take to remove these. So I guess that was 5.1. And let's try this one. 5.2. So not very much torque. Here's the BMU. Before I continue dismantling the battery, I'm going to remove these hold-down brackets and the wood blocking. That way it won't interfere with removing this front face coming off. Phillips number 3 for the screws around the edge. With hindsight, I should have removed all of these little brackets and the wood blocks before doing anything else because right now I have the black plastic cover off from the top of this battery. So, oh well, I'll do it on the next one. Next, I want to remove this big front steel cover. I see 4 screws along the bottom. I also see 4 screws along the very top, which kind of go through the steel cover, this kind of aluminum bracket on the cells, and go all the way down into the base. So we have 8 things to remove. So it looks like this green plug up on the front face is just directly connected over to the reed switch, which would be in the safety disconnect. Yeah, so it looks like the negative just has a straight shot directly to the negative amphenol connector, and then the positive is the one that gets broken. And I'm making an assumption that these are amphenol connectors. I don't know 100%. It's just a guess. So there's 4 bolts, 2 at each end of the whole cell group. So the 10S is a cell group. And then these bolts are going all the way through into the steel base. The fan blows directly in here. Looks like they have some kind of little foam gasket. The fan would blow in, and then it could disperse out between each cell to help cool it. I have taken off all the accessory components. Now we are left with just the cells. Breaking the battery down to this point was fairly quick and straightforward. At this point, before I can break it down any further, we have to discuss what the plan is moving forward. This whole pack is a 20S pack, which means it's going to have a pretty high cell voltage. Each cell is 3.2 volts, which means the entire package is about 64 volts nominal. It needs at least 70 volts to charge it. Well, that's really high, and too high for most 48 volt equipment, with a couple of exceptions out there, but generally speaking, we can't use this voltage, it's too high. The most common arrangement for this type of chemistry is to have 16 cells in series. 16 cells in series gives you 51.2 volts nominal and charges really well with all the standard off-the-shelf 48 volt components. So that's the arrangement that I want to put this into, is 16 cells in series, or we shorten that up to say 16S. Since we have 20 here, I have to decide how to electrically disconnect 4 of the cells. So what I could do is I could cut the jumper wire here and cut the jumper wire here and electrically disconnect the rear 2 cells from each cell group. or do some other combination. If I cut it right here, then this 10S cell group can still use the original factory jumper bar to jump between this cell group and this one. I'll have 16 cells in series total, and then I'll be left over with 4 cells without a dedicated purpose right away. Now in some applications, you might want the 48-volt battery, and then you might want the 12-volt left over for something else. This might be, I don't know, a tiny house on wheels. Maybe you got some 12-volt lights, or maybe you have an off-grid property and you have some 12-volt accessories, like maybe a 12-volt pressure pump or something. And maybe you want that just left over as a 12-volt battery. And that would be great. Just leave all this steel banding. There's a steel banding at the top and another one at the bottom. You could just leave the cells glued in place, and you'd have your 48-volt battery for running your inverter and a separate 12-volt battery for some accessories. Now, if you have the funds up front, you could buy 2 crates, which would be 4 modules. Now, this is one crate that I have here with 2 modules. But if you bought 2 crates, 4 modules total, you'd have 4 cells left over from each module. That would give you another 48-volt battery on top of it. So in that application, you could purchase one heavy-duty shelf, 4 shelves, 4 modules, but electrically I could connect the 4S group from here to the next shelf, to the next shelf, to the next shelf going up, and create an extra 48-volt battery. But that's not what I'm doing in this situation. I want to try to remove these 4 cells. I'm going to cut this plastic raceway and the jumper. I'll remove the steel banding, and then we'll catch in again and see if there's a way that I can actually remove these 4 cells. I'm not sure yet how I'm going to approach that because they're glued in place, but we'll work on that together. These multicolored wires are going to be checking the voltages of each cell, like right here. It's tied to the cell bus bar, but also there's a couple of temperature sensors in here. I can't just simply cut this off because I will short all the wires to each other and you'd burn out the wires. So instead we need to cut these one at a time, remove them from the plug, and I'm going to also remove this wrap here with the zip tie. This is called liquid electrical tape, and I've never tried this before, but I'm just thinking it might help with some of the loose wires here. The plugs are off on both ends, and I have a little bit of that liquid electrical tape on there. Typically when I cut off plugs like that, I go immediately to the BMS, but since I need to remove this, or at least I'm going to try to remove this right now, I can't go directly to the BMS. So I wanted to do that temporarily. All right, let's finish taking off some of these wires here. There we go. All right, so I'll just keep working this back until we get to this point, because 1, 2, 3, 4, I'm going to make my cut here. So now these wires are secured with a zip tie. We got a little bit of hot glue on there, and all the wires for the back, 6 cells, they're off to the side. 1, 2, 3, 4, and we'll cut it right here. I'm just putting a piece of plastic in underneath this bus bar to help stop shavings from going down, and I laid a piece of leather down here. This is just a welding apron. At this point, we have created 2 batteries. We have this 48-volt battery, and we have a 12-volt battery right here. Now, all these cells are currently attached to the metal tray, and they're glued down. So they're in a really nice configuration if you could use them like this. In my situation, I want to see what it takes to remove these 4 cells and just leave the 16 cells left on this metal tray. So I'm going to cut the banding and we'll see how well it's glued down. Maybe I can break free these 4 cells as a solid group? I'm not sure, but let's find out together. Notice that when I cut this, it opened up, but it didn't spring open and cause a lot of force. And we didn't see the cells expand out. My understanding is that you want to clamp the cells to hold them in place, but you're not trying to compress the cells. If these were under a lot of tension, they would have sprung out. So I'm going to try to duplicate that same thing when I refixture them after this. So over here, I need to add some form of new compression. This could be done in a lot of different ways, but I'm going to try rebanding this with a little banding kit that I bought on Amazon. So let's start by looking at the end of the cell. I removed all of the putty that was on here, mostly using this plastic trim tool. A couple of spots that look a little bit rougher, that's where I used a metal tool to scrape away the rest of that putty. I think it was some kind of thermally conductive putty because it's in between every layer, but it was not really adhesive. It wasn't really glued on the way that like a silicone might be. So it was in between all of these layers, including this plastic isolator. So I'll put this plastic isolator back on. I'm just pulling up this little plastic raceway right now. And we'll get that in place. And now before I add the metal backing plate back on, I'm going to give it a little bit of squishiness to it. I don't have the same exact kind of thermal putty because I don't know exactly what they used for that. If you do know exactly what this kind of putty is that I kind of scraped off, and if I you can see it's tears, it doesn't stretch. So if you know exactly what that is, please let me know in the comments. But otherwise, let me show you what I got. I have this chunk of aluminum heatsink left over from an old battery that I took apart. And I'm going to use this little thermally conductive mat that's on it. So I'll take this plastic isolator and use it as a guide and just put it on here. I don't know exactly what size that is, but I hope it'll be the correct size. Now I can just peel this off and I'm going to move this over to the other side. Thermally conductive mat. Okay. So now the aluminum can go right here. Yeah, so that'll work really well. So now I need to band it. This is the banding kit that I purchased on Amazon. I'll leave an affiliate link in the description below. It comes with all the tools you need, some clips, the banding strap itself, and I just thought it was a good value for everything. I got the idea for this from watching one of Lithium Solar's YouTube videos. He makes really excellent videos. If you have not checked out his channel, please do so. Seems pretty straightforward. There's a little instruction card that comes with it. So I think I'm going to try this again, and I had a thought. Maybe I'll put the tool here and have one of the legs still wrap around. So hopefully I can put the metal crimp on this side. This metal crimp, it's not exactly sharp. It is a kind of a curve, but I'd rather have this off to the side. So let's give it another shot. That was more difficult than I thought it was going to be. It took about 12 separate tries before I really felt like I got the tension correct, knowing how much to ratchet and how much tension to feel on the handle to how much tension would result here. But at this point, I feel like I've got the same tension as what was here originally. And again, it's just based on feel. Again, this is a smaller distance, so it's going to feel harder to get the same stretch out of it compared to the longer distance. But we're not trying to put the cells under tension, compressing them like in a vise or something. What I'm trying to do here is just prevent them from expanding, and I'm trying to prevent them equally on top and bottom. In the past, a lot of us have used threaded rod. In fact, I got my inspiration from my Chevy Volt. The Chevy Volt had long threaded rod through the whole length of it, so I was duplicating that on subsequent builds. But this is a nice, clean, it's a non-conductive material, this PET, I think it is. And I think the overall thing now works pretty well in this arrangement. So I'm happy with it, but just recognize that you might have to spend a little bit more time getting the feel for it. We have the main negative of the whole pack is right here. What I had taken off originally was this. It's a nut that's encapsulated in a little piece of plastic, and that went in right into this location. The original one had this plastic cut away, so I'm going to have to cut this piece of plastic for the wireway off to the side in order to get my clearance. So that'll be the next thing to do, to modify this little piece of plastic wireway. This is the wiring harness for the BMS that I'm going to use, and the black wire here is the main negative. So it has to come up to this post, which is the main negative post of everything, of the entire battery. I should have soldered this on before bolting it together, but I didn't realize that I needed to add a wire here. See, there's wires for all the other cells, but I didn't realize that when I cut this off, the voltage sense wire for this tab was actually on the cutoff side. Let me catch everybody up with where we are right now. Well, this is a lithium battery, and all lithium batteries should have a BMS, or battery management system. In this case, I'm using this BMS. It'll be the first time that I'm using this particular model from Battery Hookup. It's a 300 amp continuous model, and I did that because these cells can discharge 280 amps continuously, as well as charge. So they're pretty powerful cells, so I wanted a powerful BMS to pair with them. Probably overkill in my situation, but it'll be fun to try it out. Now the main two blue wires here, they're called B-. They're gonna come up here to the negative post that I created. But the BMS, it needs to read the voltage of every single cell. So it comes with a couple of wiring harnesses. Because it can accept so many cells, in this case 16, we actually have two separate plugs with sets of wires on each. And we need to wire all of these so that they're reading the cell voltage of every single cell. I've already connected a couple, so now I'm going to bring in and show you how I'm reusing some of the existing wires, so you can see how I'm connecting up the existing wires to the new wiring harness so that we can then connect it to the BMS. Now the reason why the BMS wants to see the voltage of every cell is because it can actually shut down the battery pack if a single cell goes over voltage or under voltage. So that's one of the benefits of this. Now this particular BMS also has a balance function, so if the cells were out of balance, meaning not equal voltage to each other, it can passively balance them. Passively balancing means that it can burn off some excess current through the resistors that are built in. We have the main negative lead, which I brought up here and is soldered directly to that little piece of copper. It looks like a cold joint, but it is stuck on there and it's not coming off. So then the second lead, which is white, is coming off here and goes to the second cell. So it ties into the blue wire, which is already attached to the jumper bus bar here. And I'm using these little heat shrink things. They have some kind of cold melt solder on them. They're just easy to work with when you're doing something like this. Remember, these wires won't be carrying a lot of current. At most, if the resistor of the BMS is on, this will carry 1/10 of an amp or something like that. So having a little cold solder joint like this is not a problem. Mostly it's just reading voltage all the time. So I've already done these three, the black and 2 whites. The next one is this white wire. So I'm gonna fish it through my fingers so I don't lose it. And it's this one. So what I like to do is trim off the little pre-soldered end. We strip that. And now I'm looking at where that needs to go. So I already did the black wire, the white wire, the purple. Next one is this pink wire. Some type of little twist. Then I get that little bit of solder positioned right over the twisted part. And now we heat it. All right, so now I'll just carry on until I get all the wires on this side and all the wires coming down off this harness as well. At this point, I think I have finished wiring all of these BMS leads. I have them taped off here so that we can test them before connecting them to the BMS. Now, this particular BMS can go from something like 7 cells up to 22 cells. So it has an odd connection that you have to make. Over here, I've got a bunch of wires here. I've got 6 different wires all tied into one from the battery. So this particular part can be very confusing. So you gotta look at the wiring diagram. Battery hookup posts the wiring diagram for this BMS, and it's pretty clear if you just watch it. All right, so now we need to test this, but I need to put the little jumper in the back connecting the 2 sides. So let's do that. From our main negative, which is over here, to our main positive, 52.71 volts for the whole pack. Now we need to individually test each wire lead. So this is the main negative wire of the entire pack. It comes over here. Now the very first lead is a little bit nerve-wracking because these pins are so darn close together. So you gotta really kind of angle it out, and you can see it's a 3.2 volts. That's for a single cell. Now I'm going to move the red probe over, but as we're going across, let's just say, all right, we're at the end of this plug and we're at 42. Jump over here, 46, 46. This is where they're all grouped together all the way down the line. The wires are grouped together until we get to the end. Now we got 49, and then the last two, 52 and 52. The last 2 positives are also grouped together. But again, this is in the wiring diagram. Always follow the wiring diagram. Don't just watch my video on it. But it's really important to check all of these. We went up by 3.2 each time. We didn't have any crossed wires. It wasn't like we were going from 6 volts all of a sudden to 50 volts. You know, we didn't cross them somewhere. So always check these before connecting them to the BMS. We're done with the wiring, at least temporarily enough, so that we can perform our first test. So we've got our BMS here, wired up to the negative post, and what I've done is run it down to my meter, and off of the inverter, which is right here, I've also got this extra set of wires going to this charger. So we're currently charging, and we should be done charging very soon. We've got 53.4 volts. And this app on the phone is reading the Bluetooth off of the BMS. So this battery management system has a Bluetooth built in, which is going to the app, which I downloaded on the phone. You can find the app to download on Battery Hookup's website. If you scroll down on the page where you buy this, it has the downloadable version for both Android and Apple. If I scroll up here, you can see all 16 cells, and we're all very close in voltage to one another. Everything's looking good. It shouldn't take too long before we hit high voltage, and I'll try to catch that when it does. So the BMS beeped and it disconnected charging. I heard it click, I heard the contactor click. I changed the parameters so that anything over 3.5 volts can balance. It had it at 3.3, which was a little bit too low for me. So we're off just a little bit. So let's go check. That is cell number 5 and see if it's reading correctly. It says cell number 5 should be 3.6, which should be this one, I think. Yep. And that's reading correctly. 3.672, 3.671. Oh, it's dropping. As you can see, it's dropping here as well. And then if I move it back, 3.50, and over here 3.50. So that tells me that the BMS is reading the voltages correctly. So we need to do a top balance on these cells. Over the last few days, I've been letting this BMS top balance all the cells. So all the cells look great. I discharged it a little bit and then recharged it. So we're at 100% and we're ready for our first capacity test. I love doing capacity tests. Now, since these cells are so large, I'm gonna have to put a larger load on it. And in doing that, I redid my whole setup down here. So we've got the Victron shunt connected with Bluetooth to an app on this cell phone. I've already zeroed out all the history, so we're gonna be able to measure how many kilowatt hours go through the Victron shunt. I've got a 125 amp circuit breaker. Everything's currently off, and I've ran this with some 2-watt wire going into my grow watt inverter that I pulled off from the wall. Just off camera, I've got a 240 volt space heater. I forget exactly what it is, something like 4,500 watts or somewhere around there. Now I'll bring the camera in closer when we actually go to start it, but what you'll see me do first is use this little resistor to pre-charge the capacitors inside the inverter. Then I will close the circuit breaker. If I was to just close the circuit breakers right now, you'd have a big surge, a big inrush of current into the capacitors, because these capacitors are dead right now. And capacitors are built inside of all inverters. Now that might damage the capacitors. They might survive, but they might get damaged. So I don't want to risk it. So I'll just use this little resistor, we'll pre-charge them and then close the circuit. We'll turn on the space heater and then we'll check it on the app and make sure that it's running well, and then let it go. We're going to attach this to one side. It doesn't really matter which side of the circuit breaker I'm attaching it to. And I'll also show you what we've got at the inverter. See that? I had this on a little bit earlier and the capacitors are still dissipating a little bit, so it looks like we have 400 millivolts right now. So hopefully everybody can still see that. We'll take the other end over here. So see, that's all it is. And I'm going to touch this on the other side of the circuit breaker. See, we have full voltage now. That's all it took, just a second. And now I close the breaker and we have full voltage. And so that was gentler on the capacitors. We'll take that away. And right now we've got 100%. We'll just turn on the inverter. There we go. You can see some watts are going in as the inverter is kicking on. You'll hear the relays click inside. Right now it's just warming up. There we go. Did you pick up on that click? and we've got 240 volts coming out of the inverter. So right now the inverter is drawing 80 watts to be on. And it's coming out of there, going to a plug, and then this shop heater. So if I kick on the shop heater, you'll see this just went up to, over 5,000 watts. After just 2 minutes, you can see that the wattage draw has dropped, and we're down to 89% for that heater, and 4,900 watts or so being drawn from the battery. That's because once the heating element inside this shop heater warmed up, it actually increased its resistance, so it drew less current. This capacity test is running excellent. These cells are 280 amp hours or 896 watt hours per cell. It's a pack of 14.3 kilowatt hours, and so this is the range that we are working in. We're almost done. The pack's about to shut off. Let's look at our history. 14.2 kilowatt hours. Are we gonna go up to 14.3? We've got 279. Oh man, we're almost there. Oh, it just shut off. And you see how the voltage just jumped up? Oh, and it shut off. Makes me wonder if I had a little bit lighter load instead of a 5 kilowatt load, could it have gotten that last point? But final numbers, 14.2 and 279 amp hours. So we almost got there. This was the very first capacity test. I'm gonna charge this up. We'll run another capacity test tomorrow and see if we get any better results. So I changed out the load. Last time I used this space heater, but it was a bit fast. This time I'm actually going to run it into this charge verter. There we go. And this will let me dial in exactly how much load to put on it. So I'm looking for about 2.8 kilowatts measured on the shunt. That will get me right at about a 0.2 C rate. We are just minutes away from the second capacity test being done. In this case, I've been using the charge verter, charging up a second battery bank, and the grow watt inverter here. This is reading 43 volts. I have it set to stop at 40 volts. We're almost there. We're still doing great. 5-hour discharge. There's been 2 times during the course of this test that I have adjusted the amperage rating on the EG4, just dropping it 1 amp at a time, just to keep it right at the 0.2 C rate. If we look at our history, 279. Oh, and we hit 14.3. Last time we only hit 14.2. And there's 280, so we did it, our second round. All right. That's awesome. So we did hit the mark on the second test. And that's not abnormal for the first test to not get all the way up there. Remember, these cells had been sitting in storage for the last couple of years, and this was the first time waking them up. We're almost there. There we go. You hear it? It's about to do it. There we go, it just shut off. Drop that. Oh, and I'm hearing that one beep. All right. That was great. So 280 amp hours. Oh, and this says 14.4. So we did quite a bit better. We're about to start capacity test number 3 on this battery. We've just turned on our inverter. And over here, we've zeroed out the shunt. And now let's go turn on our load. We're gonna go back to this heater. Right now we're drawing 5,100 watts from the battery. And as that heater warms up, it's actually gonna drop a little bit. About 3.5 hours into the test, we're doing great, 40.4. This is gonna die. It's gonna die soon. Oh, we're doing awesome. This is great. And it's about to shut off. There, did you hear it click? It just shut off. Let's look at our history. 282 amp hours and 14.4 kilowatt hours. We just wrapped up 3 capacity tests in a row. The first capacity test was just a little bit shy of the rating of these cells, but that's also the first time trying to cycle these cells after been sitting for a couple of years. Now the second 2 capacity tests all met and exceeded the rating, so I think we have a really good battery here. All top balanced, good to go, and I'm excited to get this hooked up and using it day to day in my Powerwall. There was one point where I had a glitch with the BMS. This is my first time testing this contactor-based BMS, and I had one glitch and I didn't catch it on camera. I tried duplicating it for the camera but couldn't, and basically the battery was full, the contactor was closed, I turned off the charger and turned on the inverter to start discharging, and the contactor went click click real quick. So it turned off and back on again really quickly. But we weren't in a fault condition, no over voltage, so I wasn't sure why it did that, and I wish I could duplicate it and catch it on camera again, but I can't, or I tried and I couldn't catch it. I'll continue using this in my setup to see if I see anything else like that happen. I'll say probably restrict my recommendation on this BMS to just things like golf carts, EVs, instead of Powerwall applications. But I'll keep everybody informed if something happens in the future. So moving on with this setup, now that we know we've got a good battery, I need to securely mount this BMS so it's not going to go anywhere. I need to secure the wires, do a little bit of wire management. I want to add a fuse. Now the BMS came with this fuse, but all it says is 400 amps on it. It doesn't say anything else, no brand name, can't look up any specs on it. So I'm not going to use this particular one. Instead, Battery Hookup sells fuses that are name brand fuses, really high quality. Sometimes these can cost over $100, sometimes a couple $100 each if you buy them retail. And Battery Hookup sells them for a couple of dollars when they take them out of a large module. So I'm going to use one of these, probably this one, in this setup. I slid the battery into this old server rack cabinet by notching the rail in the rear to make room. The front is still a little bit too tight. This wasn't made for a server rack, but it's so close that I think it'll work really well fitting in here. Now here's the front panel, and I need to cut 5/8 of an inch off both sides in order to make this fit. Now I'm not going to be reusing these connectors. I don't have this type, and so there's really not a strong need to reuse this front panel. I could just recycle it. But I like the disconnect right here, so that's really the only reason that I'm going to try to make this fit. Here's the original front panel, and I trimmed it down on both sides and drilled a couple of new holes so it's going to fit into the server rack. Now here are the original negative and positive posts, which I took out because these are a unique fitting and I just want to use something that's more generic. So I bought these. I've used these in the past on a couple other batteries. They work well. They're relatively inexpensive on Amazon, but it's an insulated bushing. There's a ring to secure it in place, and there's this long piece of copper that goes all the way through so it can handle several hundred amps. And it's got a 3/8 inch stud going all the way through. So nice solid connection. It'll insulate to the steel plate. So what I want to do is drill out this opening a little bit larger so that this negative post can fit in here. I'm going to add this fuse. So it's going to go right here. So I'm going to drill out at this location. That way I can secure the fuse holder. And then I'm going to drill a new hole over on this side for the positive post. So the positive post can go right here. So the BMS is attached with a couple of little standoffs. Now we'll bring these blue wires up to the negative post, and I can attach my BMS leads. All right, we should have no voltage right now, so let's double check that. Yep, so we got no voltage. That's so cool how that cams down. And now we should have voltage if the BMS is working. And we do. 53.3 volts. Building this battery bank was actually a lot of fun. I'm really happy with the way that this battery turned out and getting it into the server cabinet. But it did take a lot longer than I expected, as most of my projects do. So let's run through the numbers and find out, was it worth it, and would I do it again? Who might this be a good idea for? How long did this project take? Well, it took me about 2 weeks, working 2 or 3 hours a day on it to get to this point with one of the battery modules in the server cabinet. Remember, a lot of that time was spent filming, moving the lighting and the camera around. Also, I had to figure out how to do it because I didn't have a plan going in. I made it up as I went. So I assume that this second battery is going to take me a lot less time. So between the two, we're going to wind up having about 28.8 kilowatt hours in capacity and probably 40 hours total in the project. So for $5,000 and about 40 hours of working time, we'll wind up with about 28.8 kilowatt hours. I think that math was $173 per kilowatt hour. That's pretty good. These server rack cabinets behind me, like this one, which I got from Signature Solar, that one is working really well, but that's about $300 per kilowatt hour. So this is less. But to make it even better, I talked with Battery Hookup, I talked with the owner, and he's gonna give an extra discount for anybody who uses my discount code, which is David Paz at Battery Hookup, and this will be a temporary discount code. I think he said 30 days, he'll honor it. And we're going to drive this price down for this setup to about $150 per kilowatt hour, I think, with that added discount. That means we're going to be half the price of buying the pre-made server racks. So is it worth spending about 40 hours of time in order to get here? And I mean, I personally think it is, because I don't make $5,000 in a week. So for me, it was worth my time. These are really high quality cells, and they're not used cells. They've been sitting around maybe 2 years, so they're new old stock, but there's no cycles on them. So really good high quality battery by the time we're done with this setup. Now that math does not take into account that we still have 4 cells left over. So I've got a really nice 12-volt battery still waiting for me. And when I cut open this module, I'll have an extra 4 cells. So I could either make a really powerful 12-volt battery or a 24-volt battery, or what I'll do is I'll probably take those cells and series connect them with some other different cells that I have in the garage and create a large 48-volt battery bank on top of it. If a friend of mine was to ask me, hey, is it worth buying these modules for their setup? I'd say probably if you're in one of 2 situations. First, maybe you have a cabin or something like that where your loads are relatively small and the 14.4 kilowatt hour capacity is plenty for you for your 48-volt inverter system. Plus, the extra 4 cells, the extra 12-volt battery that you'll get out of this setup can be used for, say, 12-volt lighting in a cabin, or maybe a 12-volt water pump, something like that. And that way you keep it glued in. And the reason why I like that is because Cutting those 4 cells out was probably one of the more dangerous things that I've done on this channel in a while. It is definitely under the column of don't try this at home, folks. So if you can keep those 4 cells in the tray and just electrically cut the bus bar and have 2 separate batteries still in the same tray, that's the way to go. Now the other scenario that I really like for this is if you buy 2 crates. Now each crate comes with 2 modules, so you'll have 4 modules total. So if you can swing that from a cost upfront perspective, which is something around $9,000, then you would wind up with 4 of these. So if it were me, I'd probably buy some heavy duty shelves, more like the pallet racking type shelves. Electrically, I would disconnect the 4 cells, but wire them one shelf to the next shelf. So I'd wind up with 5 batteries total, 5 48 volt 16S batteries. Now at that point, with 5 batteries, I would probably go with the smaller, less expensive BMSs from Battery Hookup. These are 100 amps each. And that means that with 5 batteries, you'd have 500 amp capacity. Now that 500 amp capacity is plenty of amperage for most of us going off grid in our home inverter systems. So that's kind of the 2 situations. Now, if you're in the situation where you got to kind of cut the cells out or remove the cells in some way, well, that adds to the time, the difficulty, and adds to the risk, the danger. This was not something that you want to be tackling. I like testing my limits and seeing if I can do it, but it's not something that you'd want to do if you can help it. Let's run through the math real quick on the situation where you buy 2 crates with 4 modules. So you'd wind up making 5 batteries in the end. So you'd need 5 BMSs, and it would wind up being something about $9,200 from Battery Hookup before the discount or shipping. All 5 batteries together would give you almost 72 kilowatt hours of capacity, which is fantastic. That's more capacity than 2 of these racks. And then after the discount code and buying some of the accessory items like the terminals, you'd wind up somewhere around $120 per kilowatt hour total. All said and done, after shipping and after the discount code. Now, personally, I think that's phenomenal, given that these are not used EV cells. These are brand new cells with no cycles on them, but they are about 2 years old since the date of manufacture. So if you have the funds to be able to do a situation like that right up front, I think that's a fantastic way to go. So in the future, I'm going to be adding some angle iron rails into this server cabinet. I'll be converting the second module, put it in here. Then I'll parallel these together with some little bus bars inside the server rack, and then run 4-aught wire out to my central bus bars, which are up on the wall for the inverter. So I'm going to be paralleling this server cabinet along with the cabinet behind me, which I have the batteries from Signature Solar. So all of those can parallel together because they're all 16S lithium iron phosphate. They all share the same voltage curve. There are a few nuances when you start paralleling different amp hour capacity cells, different internal resistance. And we can get into that if there's enough interest in the future. But thank you everybody so much for watching. I hope everybody enjoyed the video. And if you do, please consider subscribing and hit that like button, share the video. And at this point, I'm going to start working on the second battery module and get some iron rails in here to slide the next one in on top of it.